Okay, hello everybody. Thank you for joining the workshop. And I hope you're in the correct workshop because this is the mzmine one. So the workshop today will be basically on untargeted metabolomics and data processing in mzmine. We will have a short introduction to what mzmine is about, and then we will go into a hands-on session. And the workshop here will be held by me, Robin, and Corinna. My name is Steffen. Robin is the one doing the pantomime here in the front. And Corinna, in the end, will also give you an introduction to library building in mzmine. And so Robin and I are basically the developers, or like some of the developers of mzmine, and Corinna is the core facility lead at the University of Vienna, and also put a lot of work into spectral library building in the past. And Tomáš also was supposed to be here, but unfortunately also has other stuff to do, so we will have to make up for that. During the hands-on session, if you cannot follow along or you have some problem, then please feel free to raise your hand. We have some amazing helpers on the side that will try to assist you. And otherwise, please don't hesitate to raise your hand and ask a question or something. So, and now I would say we just start with the workshop. And basically, mass spectrometry data, as soon as you acquire it on your instrument, basically on high-res mass spec, you acquire mass spectra, either in, for example, in LC or LC-IMS mass spectrometry. Then during the processing, you, for example, look at one specific mass range, you extract the ion chromatograms, and then in the end you want to basically resolve the individual features from these chromatograms. And similarly, there's also the multi-imaging or imaging workflow in general, where you also acquire mass spectra and extract images from this one. And basically the thing is, what we want to say is, you acquire spectra and you need to extract either images or chromatograms or features from it. So the workflow is similar, but not totally the same. But we are trying to build mzmine as a platform that can basically process any type of mass spectrometry data, be it from, for example, from LC, from GC, from MALDI, from direct injection, and then the detector being, for example, an Orbitrap or QTOF or an FTICR, or, for example, also low-resolution quadrupole instruments. And so basically, mzmine is a platform where you can process your data of most vendor formats. We're trying to be like super fast, so that you don't have to wait for hours for your results. And we're also trying to be easy to use and trying to help you to get the most out of your data. And so mzmine is an academic, or has been an academic project and has been alive for quite some years now. And we actually had our 20th anniversary last year, because the first poster note of mzmine was in 2004, the first publication in 2006. And as you can see here, it's really used a lot throughout academia. And then with mzmine 4, we really try to refine and optimize a lot of the stuff and make it way more user-friendly with the mzwizard, which we will also use today during the hands-on session to make it way easier to process your mass spec data, even if you're not a complete expert in the field. And what's really nice is that the software is open source. And it's also free for all academics to use. Just sign up, make an account, and basically then you can automatically use the software. And for example, if you're a developer, we are also trying to get your contributions. For example, if you have some idea that, for example, for some more specific processing that you need for your application. Since the software is completely open source, you can just download the source code, do some modifications, and in the end, we also really like to help you to get it like everything running and integrate it maybe even into mzmine to the full project, so other people can benefit from it as well. And basically what you can also see here is that even in the, or like especially in the past few years, we've basically invested a lot in the development, and I think the graph speaks for itself that the software has progressed a lot even since the release of mzmine 3. And also what's really nice is you can use it on Windows, you can use it on Mac, you can use it on Linux, you can use it in user interface mode, you can also run it on a server if you have really large data sets, and completely optimize the automate the data processing workflow. And in the recent releases, we sped up the processing really a lot. So if you're still on mzmine 2, I don't know, is someone still on mzmine 2 or mzmine 3 even, then totally please try the latest version. It's way smoother, way more stable, and also way faster than everything you have in mzmine 3. And also, some people have struggled in the past with the RAM consumption of mzmine. So, for example, that you were not able to process large data sets, and you can see Robin and me here trying to put a lot of effort into optimizing everything. So we basically did a lot of progress there. So with the recent 4.8 version, I think we made a huge leap forward in that regard as well. And basically you can just sign up if you're an academic, and use the software for free. And later on, for example, in the software, what you can do is you can load in your raw data. You can click through the software. You can do some basic raw data browsing, I would say. You can do some basic quality control. You can compare different runs. Along your HPLC, can check if everything's stable, and you can also, of course, then do the feature detection workflow in mzmine. And what is really nice is that the whole workflow is really modular. So, for example, for usual LCMS data, we would have just a data import. We would do some spectral processing, for example, some centroiding, some thresholding, then build chromatograms and resolve these chromatograms into individual features, and then also align and the features across different data sets, across different samples. And since the software is so modular, what you can also do is, for example, if you use the ion mobility spectrometry in your data analysis workflow, you can basically keep your regular workflow and just plug in some extra steps for the ion mobility dimension. And then, of course, later on also add some, for example, ion annotations, molecular networking directly in mzmine or on GNPS. You can exchange the data with Sirius and also do some statistic workflows with the FBMN stats or also in mzmine. And back in the past, when we didn't have the wizard, you would have to do that manually, or like every step individually. But with the mzwizard, you basically just tell us, okay, I had this instrument configuration, for example. So, for example, I used an HPLC with an Orbitrap or a GC or a multi-ion source. For example, I also used some ion mobility spectrometry or not. And what it's also really easy is you can then say, okay, I want to build some spectral libraries. I did data-dependent acquisition. I did data-independent acquisition, and so on and so on. And it will basically just give you a predefined workflow, which you can, if you want, adapt and really specialize and customize to what you need. But it's also really easy to get some first results just from setting up the workflow as you would have in your lab. And then in the end, what you get out of the mzwizard is such a feature table. In here, basically each compound is in one individual row. You can see the chromatographic peaks here in the shapes. You can directly across, for example, your sample metadata. For example, you treated some microbes with some chemicals or some drugs, and you can see, okay, maybe this one is up or down regulated, and so on and so on. And you can directly see, for example, the compounds as what they were annotated. And you can, of course, also, or like these annotations, for example, can come from spectral library matching. So basically in here we would compare our experimental spectra to a reference spectra. But what's also really nice is you can also do directly molecular networking in mzmine, which basically means that you can trace individual compounds based on a spectral similarity. And this means that, for example, we might not have adrenaline in our sample, but we might have dimethyl adrenaline. And this would basically mean that some signals would be shifted by the mass difference of the modification. And then these spectra look similar, either because they have exactly the same signals or because they have the signals shifted by the precursor mass difference. And then we can basically build a network, and we would know, for example, this compound down here is adrenaline, and this one we didn't directly identify, but we know it's really similar. And this already gives us a lot of information. For example, by this one, we can then map the chemical space. We can have our annotated compounds here in pink, and we can have all the unknowns that we don't actually know what it is at the moment, but we can basically say, okay, because it's so closely correlated with, for example, the terpenes or plasticizers or carbohydrates, we could basically propose, okay, this might be similar compounds. And then what we tried really in the past is to make mzmine even more interactive, because most of the time you would export your data and then do some statistical analysis in a different software, but then you're not connected to the actual raw data anymore. You can't really say, okay, does this feature make sense, or is it just some spectral noise or something? And this has really been like one of the latest additions, where we basically connect the statistics dashboard. This is a PCA plot with the loadings and the scores plot. And as soon as you select something in here, you can directly see, okay, this, for example, this compound is really significant in the PCA, and it's connected to a lot of other compounds in the molecular networks. And then we can basically say, okay, they are also, for example, significant, or they are way less significant. And the molecular networking, I would say the classical way is the modified cosine molecular networking. But we have some recent additions that use some machine learning algorithms to do a different kind of molecular networking, which then serve additional purposes. You can get some more annotations. And there's actually 2 talks during this conference. One is on Wednesday by Roman. Roman is also sitting over there. And I think the talk will be great, so you should go there. It's in session 19 at 4:10 in the afternoon. And then there is also MS2 Deep Score, which was developed by Nick, and it's also in session 2.5 on Monday at 5 p.m. And also, what we would like to highlight is that we have really improved also the molecular networking speed in mzmine, and it's also way faster now. So please try it out if you feel like it. And then we also have, since we don't have just spectral similarities, but we also may have, for example, illusion profiles, and we have different ions and in-source fragments. We can basically also build some additional layers on top of the molecular networks, which will basically give us an additional connection, for example, because if we may have redundancy by having the M plus H and also the M plus ammonium and also the M plus sodium ions in there. And this basically means that the same information for a compound is represented by addition or just different molecules and different features, but this allows us to get rid of that redundancy and be less cluttered in the molecular networks. And for example, here you can see some examples that were discovered by Annika, and basically it allowed us to basically reduce a lot of the redundancy, because we were able to find out that a lot of these compounds or a lot of these peaks were just some internal in-source fragments or different ion types. And we said that mzmine isn't just for LC-MS data. You can also process, for example, GC-MS data. We can do spectral deconvolution. Basically, in the wizard, you would just set it up as a GCEI workflow. And then you can do the spectral deconvolution, you can do the statistics, you can do the spectral library searches also directly in mzmine. It also works for multi-imaging data. You can also do some co-localization analysis. So for example, if you identified one compound, you can see to which compounds it is also co-localized to. And so we are trying to be like super versatile. And of course, we cannot cover everything of that in this workflow. But there are a lot of YouTube tutorials. If you just search for mzmine VMO series or the mzio YouTube account, then you can basically find all the old workshops that we did as a kind of a public archive. And so, for example, we have one on lipid annotation by Ansgar and on GC and multi-imaging, and my workshop on ion mobility, and so on and so on. And I think with this, we will start into the live demo. And for that, I will hand over to Robin.
Hi, I'm Robin, and I'm back. So, I don't know, someone asked if we also share the slides, and we decided to just do so right away. Don't download them now, because it's still going to put some strain on the internet, but you know it's the same folder that we shared with you, where there was the data set. You're also going to find the slides, yeah? So you can just download them. And with this, I would like to start the hands-on session, so you can all boot up your laptops and already start mzmine. Typically, you know, when you install mzmine, it runs on all the different platforms, but at the same time, you can either install it, and of course, some people have some like restrictions for their laptops, or you know, but we don't need any elevated writes, so you can also go with the like portable version. Yeah, so you can also download mzmine. This way you can also have multiple mzmine versions on there, just in case, let's say you have like an old study that was done with mzmine 4 point something, and then you want to update for your new study, but also want to have like the old version just in case you need to reprocess and really have the same results. And so you boot up mzmine, it should come up, and the latest version is 4.7.8. I personally, I know it's tough, right? Updating software always takes some, you know, you have to download, you have to kind of trust that it's going to be better. And also, I can only say, like, we make the software more stable, and we put a lot of effort in, like there's, of course, there's always going to be some bugs that we kind of iron out, but also the reporting and everything we try to make better, that if we update, and there's going to be a change, let's say, you have your configuration, and you load it, that the new update is going to tell you, this has changed. Like, that's not going to affect your analysis, or maybe look into this module, there's a new parameter, or there's a change to the parameter, and that was actually like a more major change. Yeah, so we tell you. And if you open mzmine, there's usually the welcome page. And with the welcome page, you have many buttons that you can click, and honestly, sometimes just do so. Like there's the YouTube, there's the documentation. Documentation also runs on GitHub. That's a platform that coders know and use, but honestly, it's actually for everyone. It's actually quite easy to get into. Because the documentation is just written in Markdown, you can always just go and basically propose some changes. Let's say you find that your data needs to be treated differently, or like data, let's say conversion. There's something in the documentation already, so you can always go and search for data handling, data conversion, supported formats, and then there is some different sections on different data files and maybe some issues. And we, like, if you find something, just propose a change and add it to the documentation. It's a community effort. So with this, in mzmine, the first thing we have to do is sometimes you will see on the top there's a bar that tells you the temporary file directory was not set yet. Then usually just click on set the temporary directory. If you already click to hide it, you know, you can always go on the project and preferences, or there's also the preferences down here, so the little gear icon. And in here, honestly, just you can change many things, and especially, let's say, the formatting of some values. If you feel like retention time should have more digits, more significant figures, you can change that. You can just up them, and it's going to change in mzmine. And then in general, that's actually some important parameters where you have the temporary file directory, and I typically put it somewhere on a fast local drive, because if we want to process a lot of mass spec data, it's quite heavy. There's a lot of data to be processed. We actually use memory mapping to speed up the process and being able to process thousands of files, like thousands of gigabytes, just on, let's say, a laptop or a data processing computer. And so please always just do so. You can like change it by clicking on the 3 dots and then just selecting a folder like temp mzmine I created, and I will just select that folder. And yeah, just make sure it's on a fast local drive for best experience. And then you can just close this, and the start is then that you have to make a user account. So if you open this, you're going to see there's a couple of users already for me, and maybe for you, you already get like a login screen where you have to create a user account. And if you do that with your academic email address, you're going to get a free academic license directly. And if not so, you can always reach out to us and basically say, I'm from this university, I'm from this institution, this is our domain, and then we basically put it in our academic program. Just tell us like what kind of university it is, and so we have it for our records, and then anyone after that is basically going to get the 1-year license. And if after the 1 year, you only have to basically say, I'm still at the university, or maybe you changed university, so you just update your profile and revalidate that you still have the academic email. Everyone else directly gets a trial account. So if you work in a company and you want to use it for commercial use, then basically you get a trial account, and you can always reach out to us to get a demo, or basically like get it extended or figure out some way. For now, we also uploaded a user file. And this user file is actually the like easy way of how you can use mzmine also offline. So maybe you already downloaded this user file, and you can just drag and drop the file into mzmine. So either, if you already have an account, just go on the user icon here, or on the top, user, sign in, sign up, and you're going to be able to like sign in with your account, or just drag and drop the file into mzmine. And so please all kind of log in to your account, or maybe drag and drop the mz user file into mzmine. And again, it was shared on the same drive. It's a very small file, so you can definitely download this one. So with the document that came, there was a link to the user file. It's basically the dataset link as well. Or also down here, the user file directly. So if you go there, there's the workshop, Metabolomics-25 mz user, and you drag and drop it into mzmine. Okay. Usually, hands-on goes kind of slow, but once we get the data processing done, you can kind of play around. So anyone has some issues with the user, please just point up, and there's a couple of people helping you. So just point to them, and maybe they can also distribute just a little bit in the room. So from here, we want to start the processing, and this is done in the mzwizard. So with the mzwizard, this is our way of really just streamlining how you build up the workflow like you do in your lab. We're going to put together a UHPLC method with, there's no IMS involved. This time we're going to use an Orbitrap mass analyzer, but that doesn't matter so much. It's only different presets. And then we have data in data-dependent acquisition, where we have MS2 spectra for like the top 5 precursors. And I am going to load a local preset. So, and then we're going to set it up together. So this is usually also how you're going to share this. So there's local presets that you define for your, let's say, 10-minute reverse phase gradient, and for your Q executive or timsTOF or whatever instrument. And then later you can mix and match these different methods and then configure mzmine quickly. So from here, first thing is we have to select the files. And by like selecting the files is, first of all, you have to select here UHPLC and Orbitrap. And then in data, there is the metadata file. So you have to check the metadata file. And then here, we have to find this file that we shared with you in the data folder. If it is zipped, I have to disable some things here. Okay, so if it's zipped, you have to, of course, unzip your file first because we cannot read your metadata file from there. But the metadata file actually just contains the, let me see, it's just a TSV file or CSV file, so a table with metadata with the file name and the species and condition of the samples. Yeah. So we're going to load this one. We can just go, and if we have the file explorer, I can just drag and drop it into this box. But honestly, maybe easier, you can also just go on select. Yeah, if maybe you're searching where I open this, again, the mzwizard is available either from the start screen, there's a button, mzwizard, or you can always find it on top. There's, let me see, wizard, processing wizard. Yeah, so you can always find it also here on the top, the mzwizard, and open this screen. So again, you change to UHPLC Orbitrap, and then in here, data, we're going to select the metadata file just by clicking select and finding this metadata underscore pa.tsv file. Okay. And then in the same folder, there's actually the raw data files. And you can always just go on, for example, select files, and then you're going to have the screen here. So I can just select with Shift, for example. I can Shift select all the files and say open. Or sometimes I feel it's easier to just click on all mzml files. And then I only have to select the folder in which I have these data files. So 20 years of mzmine and select. And it's going to get all the mzml files in that folder. Okay? I know that Steffen typically, he prefers to just drag and drop again. So you can always also just drag and drop the files. So you select all of them, drag and drop them into this box. If you drag and drop them into mzmine, you're going to see that it already starts importing the files. But don't worry, I mean, we want to import them afterwards, right? So that's also going to work. So you select the files, you select the metadata, and then we have to set up some of these parameters. And again, if you have struggle, you can always ask those people, and also you can just lean back and basically listen to my voice and just follow along watching. But I kind of still want to get some people that really click everything, so it's going to take some time. In UHPLC, we have to kind of look at our chromatograms and maybe cut out some parts, right? Maybe there's, in the front, there might be just like we divert to the waste, maybe we want to cut out this, and maybe at the back we have some clean out step in our chromatography. So for doing this, we can open the raw data overview, and for this I will just double click on one of those samples. So in the MS data files, first, you have to import the file. So again, how do you do this? You can just have the files in your Explorer. You select all of them, and you drag and drop them into mzmine, and it's going to import them. Or you can also just, like from this list that we made, we can basically also go to import MS data, and you have the same thing here. Yeah, so typically you can just go from here and basically have the import MS data and then also select the same files. So we select the same files, or click on select files, select everything, or we go on all mzml files and then just select a folder and go with this, and it's going to be selected and import. But if you have those files, and like everyone has the files who wants to follow along in mzmine on the left side, so you can already play around by just basically double-clicking one of those files, and it's going to open this raw data overview. And in the raw data overview, we try to make it interactive so that you can have the chromatograms on the side. It's typically configured to be a base peak chromatogram, so the highest intense signal is going to define the shape of this chromatogram. You could also change it to TIC here down in the settings, but honestly, typically either one is fine for just exploring your data. If I want to zoom in, I can always just like drag a box and zoom in. I can always drag the axis to basically move it. I can drag it to zoom in. And also you can always combine the modifiers. So if I combine it with control, I basically zoom in. I can use the mouse wheel, for example, to just zoom in on the signal. And if I click anywhere, it's going to pull out the spectrum from the sample at this position. And it's also going to highlight the spectrum in the bottom. And in the bottom, you see the spectra, like scan number. You see that it's MS level 1. And you also see that, say, the precursor MZ for the MS2 scans that were acquired afterwards, and something like the fragmentation energy and so on. Yeah, so if we click on any of these data points, you can see the spectrum. I can zoom in. And of course, one thing we might want to make sure is it actually centroid or profile mode data? Honestly, I've seen people like just process profile mode data as if it was centroid mode data. We try to warn you, right? Sometimes we also don't know, because if the metadata doesn't tell us if it's profile or centroid, so we have to kind of analyze it and find out. But still, like, you can just zoom in the spectrum. I can like hold control and move the mouse wheel. And if there's really just one line and there's nowhere, like never like a peak shape to be seen, it's already centroided. And that's what we did here. So it's raw files from Thermo. We went through MS-Convert for the conversion. And in mzmine, the conversion actually happens in the background. So you don't need to handle MS-Convert. You only install the latest version of MS-Convert, or maybe the version that works best for you, or the Thermo raw file parser. And then mzmine will pick it up in the background and will use it for data conversion for you. And it's also, again, in the configuration, you can set up if you want to keep these mzml files, so we only convert once and you're going to have the mzml files, or if we should just convert it and then basically scrap the mzml file. Up to you. So in here, more things that we can do is we can also, of course, look at other signals, because if we click anywhere in the chromatogram, it picks the highest signal and shows the shape. And if we take one of the isotopes, I mean, it should have the same shape, right? That's basically one analysis that we can do. I click in the spectrum, get a different mass already visualized. I can click on different other masses and see maybe they're a little bit shifted. And I can kind of look at the peak shapes. I honestly think it's very important that people actually look at data at least once to make sure your analysis is actually running like you hope it is. It's quite tedious to do like too much manual, and I really just do it quickly. But one thing is also sometimes you want to maybe just compare the QCs already just by the eye. So we can click on this little checkbox on the top, raw data overview, checkbox. If you see the checkbox, it usually means that if I now click into any other sample on the left, it's going to pick out the chromatogram. I can pick out the spectra again. And if I actually select multiple, you're going to see that we overlay multiple samples and also multiple spectra if I just click into any of those chromatograms. And now we can actually see that there's a shift in retention time for 2 of these samples. And if I basically kind of like single out those samples by just clicking again 1 and 2 and maybe 4, I can click somewhere and I see that it's actually the first 2 samples that are shifted. Yeah, it's the first 2 that are shifted, and I can see that by just like kind of going through the samples a little bit here. So during the analysis, we might want to exclude those, of course. And so coming from here, we can now optimize the wizard, and this is only like just getting an idea about the data. But now we can optimize the wizard and then directly start with the processing. So first we see that here, again, we divert it into the waste, and then afterwards we have this little hump that maybe we want to cut out. So we can switch over to the wizard, go to UHPLC. It's important you just keep the wizard open in one of the tabs, UHPLC, and in here we could, for example, cut out the first 0.3 minutes. Yeah, so if we look here, it's a bit more than here. There's a little gap then, and then we're gonna just cut out the 0.3 minutes at the start, and then at the end, honestly, we can either just keep the whole thing, or we could say, this one looks like a clean out step. It's not my data actually, so I don't actually know if it's a clean out step, but it kind of looks like that. So we could just say, okay, we're gonna cut it at 8.3 minutes or something like that. Yeah, I personally think, especially if you want to do statistics later on, it's sometimes better to, of course, not over-interpret the regions in your chromatogram that have very poor separation. So we can cut out the 8.3 minutes. The next parameters are actually not so important. Like the minimum consecutive scans is kind of important depending on what kind of mass spectrometry you do, right? If you have a very fast chromatography and your scan rate is very slow, you don't have so many data points on your peak. And I will just show you how to kind of get that. In that chromatogram overview, I can click on a peak. That's a big one, right? So it's going to have more data points than maybe some of the smaller isotopes. I could maybe pick one of the smaller isotopes, and then in here, you're going to see I can kind of count the data points, like 1, 2, 3, 4, 5, 6, 7. But I can also, for example, just go somewhere for a smaller peak, and I can just click the keys on my keyboard, and it's going to jump from MS1 to MS1 if I go left and right. And if I go up and down, it's actually going also through the MS2 scans. We're going to see on the side, there's the MS2 scans. Of course, they look much different to the MS1 scans because we select a precursor and then there's much like less signals. But from here, I can say there's actually okay number of data points, but we did acquire the data in DDA, so maybe we set it up for 6 data points. Yeah, so you set it to 6 data points here, and then with the approximate feature full width half maximum, we can again click on one of those signals and just estimate from here what is the full width half maximum, and it is around 0.3 or 0.4. So we could now go in here and say 0.03 as the full width half maximum. And this is important for the feature detection later on. There's other retention time tolerance down here. There's one retention time tolerance within your samples. Like in the same scans, if we have isotopes and if we have adducts, they should have the same retention time, but sometimes they do have like a little bit of a different shape. They should not, but usually we still have to have like some tolerance how we pick the like isotopes and the adducts of the same molecule. And this is the intra-sample tolerance. It's usually quite low, maybe the same like the full width half maximum, because when the peaks get wider, that tolerance also needs to be widened because like getting the top of a peak, of a wide peak, is much harder than if it's very narrow. Then the retention time tolerance sample to sample is actually important for the alignment. It very much depends. Do you have, like, did you run it in one batch? Maybe you ran it in across 2 years, 2 batches, the column is different, like a new column at least. So this is a very important thing that you kind of have to optimize, especially in like those multiple batches. But one thing is you could now, for the first run, basically just up this number, you can increase it, and then mzmine is going to tell you like if there was like a good alignment within this and what the maximum difference was. Yeah, so when you run it once, mzmine is going to tell you what the maximum retention time difference was for your compounds. For now, we can just leave it at 0.1. With Orbitrap settings, actually, you can just leave them to the default. There's the positive mode data. If your data sets only have one polarity, and this files actually is only positive, so we could keep it to no filter. If it is polarity switching, positive, negative, then please select one of these filters here, and then you have to do the processing once for positive, once for negative, and then in the end, of course, you can try to kind of merge these results. But we have to process them separately. So here we go, no filter, factor of the lowest mass detection. So we're going to filter out some noise. For MS1, the noise is typically like a little bit higher, and we can filter out more signals with like 5, and then for MS2, 2.5. It's the default settings, you don't have to change. And minimum feature height very much depends on like how low you want to go. Yeah, so we're going to set it up to 5E5 for Orbitrap. That's actually kind of a medium size. You know, it's like not too low, it's not too high. It's already filtering out some smaller signals, but this just means we need to have a feature of 5E5 in at least like 1 or 2 samples, and then we're going to recognize it as a peak, and in the other samples it could also be lower. Yeah, that's okay. And then these tolerances, we're just going to leave with the default. Now you would say 10 ppm for Orbitrap is much too high, but this is actually the tolerance scan to scan. Yeah, like, and if we want to find the different signals from like the first scan to the last scan and build a chromatogram, we have to be a bit wider, let's say. And within that tolerance, usually there is also not many things that are going to interfere. So we just leave it to the default. And filters, we're going to set to remove. So in the filters tab, there's original feature list, remove. Then minimum samples per aligned feature. We do have some replicates here, and we also do want to do some statistics, so it's always good to have maybe here like 3 samples, or you could also say 10% of your samples need to have a feature to be considered for the downstream analysis. Yeah, so you can set up this, and honestly here we're just going to go with 3 samples and 0%, but the percentage is quite nice if you scale your analysis. You go from, let's say, tens of samples to thousands, and then the percentage is basically going to capture that much better than if you say, yeah, 3 samples. Yeah, because of course this kind of filters out noisy peaks that we only spuriously detect in some samples. And only keep features with 13C. We're going to check it for now. So we check this feature. It's basically going to evaluate the 13C isotope pattern of our features. I'm going to say this one looks, it could be something real, like something of natural occurrence. If you do isotope labeling, of course, you would have to uncheck this and you would have to process a bit differently. And then in the annotation, I did send some different libraries, and this is actually the wrong ones. Oh my God. Yeah, I already updated this on my side. So I have to find it as well. Let's see. So I did send to you like a JSON file, right? Let me see. What did we do? So there was the spectral library, and it's the Mona spectral library. There's a lot of different libraries you could use. GMPS, MassBank North America, MassBank EU. Honestly, they try to exchange spectra, but they still have kind of like a different coverage sometimes, and they have different let's say, routines of like filtering out spectra. But in general, all of them work. And I just have to find it myself, so you can already try to select the library.
For you, the library should be in the same folder as the dataset.
Yeah, you should have downloaded it, and if not so, of course, then it's too late, but you can just go along without the library and it's still going to work. Let's see. This one, right? Okay, so it's a JSON library. Then I can drag and drop this in here, or of course I can go on select files. And this is already going to just filter out the spectral library formats. JSON is just a very like general purpose format. You're also going to find JSON files for everything else, like CSV or TSV is very standardized, just an open format. But with the JSON, this is the format of Mona. We can select it, and we also check this annotate lipids, just in case if we have some lipids, we can see them. And then in the end, there's the DDA, which is the workflow. Later, we're going to see there's also library generation, data-independent acquisition. So if you do something else, you can always just change it here. But with this, the only thing you have to do is select an export path. Selecting the export path again, you just go on select. And in here, you select a folder, and you also need to select a base file name. So we can say, for example, Metabolomics results. And this is the base file name, and mzmine is going to generate a lot of different files and always going to put something to it like GNPS export, series export, the feature table, the mass spectra. We export many, many things and just put some suffixes to it. So again, DDA, you select and you just select like a base file name and write it in there. And make sure it's a file path that's actually reachable on your computer or somewhere. So I will just reiterate. We did put the files here. We did put the metadata file. We set some parameters, but even if you miss that, it's gonna work. And then the spectral library file, we also selected in the annotation tab, and it was a JSON file. And then in DDA, we only selected like a base file name, a path on your laptop somewhere. And from here, we can go on create batch. And you're going to see that from this like setup, we generate a whole workflow for UHPLC, MS, DDA workflow. Yeah. And there's multiple steps in there, like importing data, processing spectra, everything in here, and a lot of different export steps. If you don't like some of them, you can now just go and like just delete them, right? You hit the delete key and they're gone. You can reorder them. You can set different parameters, but in general, the idea is you create the batch, and from here you should be okay to just click OK, and it's going to run the batch. That seems like it took a lot of work, but actually what we did was we drag and drop the files in mzmine. We set up this batch. There's a couple of parameters, and those are presets, right? We give you some presets for Orbitrap, but if you tune your instrument differently, you can run your instrument at different resolutions. You can tune it for different analytes. It might need some tuning, of course, right? And especially the chromatography, if you do like a 10-minute gradient or a 30-minute gradient, you definitely just need to change the full width half maximum, basically, of your chromatography. So in here, we can always click on the task on the bottom, or there's also the task manager usually open from the start. And you're going to see that mzmine automatically parallelizes all the work. So we have so and so many samples, and they're being run each on like a different thread on your computer. So if you have a CPU with a lot of threads, it's going to be faster. If you have a fast local drive, we offload data. So the spectral data, the feature data, even the data in the feature table that we're going to see is all offloaded onto disk. So you don't need, let's say, for 100 gigabytes of data, you don't need hundreds of gigabytes of RAM. Yeah, you only need like a fast drive, and then we can process the files. And for me, it's already done. And I can always, like in the bottom right, there's this like used memory indicator. And Java, like mzmine is Java, and it's basically always going to grab a lot of memory if it's available, because then it's faster. But if you click on that bar, double click, is basically going to clear out the memory and going to tell you, I only need 600 megabytes to store all, like to visualize all that data, to also have the feature tables. And if we go over from MS data files to feature lists, we can actually just double click on any of the feature lists, and we're going to see that there's a lot of results, there's a lot of data being stored, and it only took like, I don't know, 600 megabytes for the spectral library, the data, the feature list, everything in memory. And of course, this is a small data set, but now you can scale it up much more. And so if you go feature list and then double click on the table, it's going to open the table, and on the left, typically you have, let's say, the ID, which is the row ID from mzmine. All the exports that we do, they typically have this row ID. And if you develop your own method, if you use GNPS, Series, any other tool, they typically still retain this ID, and you can merge the results. So you can bring in the results from other tools, and you can basically merge them in, let's say, Python, in Excel, you can always go back and find this was the feature with the retention time, and so on. There's now box plots. There is some statistics on alignment, and I guess you don't see that because I already changed my table. You can personalize your table if you just click on this plus button, and I hope most of you are actually done with the processing. Okay, yeah, it was just going fast. My laptop is quite good, so I was like, it could take a bit longer, but usually it's, I would say, quite fast to just process these files. And so if you open the table, there's this plus, and in this plus there's a couple of like toggle things to like turn things on and off. There's a lot of check marks, and you see there's all the data, all the results that you can basically visualize in the table. So I could say, for example, toggle shape columns, and then it is gone. Toggle shape column, yeah, somehow it was off. And if I now just drag the shape column, you're going to see that there is all the different samples here. And now we actually have like, we have the chromatograms, and they're actually not chromatograms, they are separated features with retention time, with MZ, with all these things. And you can see that the color here, for example, matches up. So we know that gray already corresponds to some metadata. We can see that if we just click on this little thing here in the box plot. We can see that there was species and condition in the TSV metadata that we loaded. And I can change over to condition, and we're going to see that in gray, there's actually, the colors don't correspond yet. The gray in the beginning is always the blanks, and the magenta is always QCs. And now I want to actually make it match up with the box plots. Yeah, so you see the box plots don't match currently with the colors, but we can do so by just going to data files. And maybe if you have loaded the metadata and data, you can actually all do this. So I can just go here, and if you want to search something, like you want to do any analysis, you don't know if mzmine can do it, you can always Control F for search. Like any other tool, Control F, search. Or maybe double shift. Yeah, so double shift, Control F, you open this little window, and you can search for color by metadata. And color by metadata, if I hit enter, it's going to open this setup dialog for the parameters. And in here, we have metadata grouping. I can click on this box, I can show the parameters, and then in here, we have either sampling date, or we can type in condition, and if I start just writing condition, it's going to show that we loaded some metadata and a column with condition. You can always check, there's like this little button, sometimes, there's a button, just click it. It's going to bring you to the metadata, and in here, if you're missing condition or species, then maybe you didn't select the metadata file, but typically if you load it, you should have your personal metadata for your samples. So I will just do this. I have condition, I have the coloring, and then I will just hit OK. And it's actually coloring all my samples. So now we have gray, orange, blue, and green. And if I open the feature table again, so I just go over to feature list, I double click on the feature table, it's going to open, and in here we can show the condition. We can again also show the sample, the shape column. This one, the shape column. It's again on the plus that we click. This plus, shape column. And then in here, if I scroll through, we're going to see that there's a lot of green. Green is actually the media. So it was not really blanks. It was the media blanks. And of course, there's a lot of compounds in there. There's a lot of nutrients. There's a lot of small amino acids. And those are actually the ones that we detect here as, of course, first of all, being quite dominant first. If we go through, there's also going to be a lot of other compounds. So there's the black ones and the blue, which is then the QCs or the different strains of microbes. But this is only like some part of the statistics that we can do. So in here, you can now always say, let's say, I want to see more statistics, so I could double click on one of these charts, so one of these box plots, and it's going to open the statistics dashboard. So either you click on the box plot, or again, if you just want to search, Control F, and you search for statistics. And there's the statistics dashboard. I hit enter. I have to select, of course, the feature list that I want to look at. And then in here, you're going to see that there's, on the one side, we have the scores plots with the samples actually mapping together. We can also add the sample type. Sample type here was actually picked up automatically because in the file names, the files are actually named underscore QC, underscore media, or underscore blank. And then we pick up that those are actually blank or QC samples. Everything else is first labeled as sample. And of course, you can provide metadata, so you can overwrite this and just say this is actually blanks. If we do so, we see that there's actually clustering happening. And also in the coloring here again, we can type in condition. And in there, we have also the media, the QC, and the two strains of our Pseudomonas. And then we have the loadings plot. And the loadings plot is, of course, much more interesting because there's orange and black dots. Those are features. And each of these little scatters is a feature where we can, again, just click and see it in the table. Within the table, again, I have to kind of get rid of the alignment column. You're also going to see there's a structure annotation. And the structural annotation comes from the spectral library match. So in here, we can see there's different compounds being annotated. We see directly the box plots. And if we also want to compare two groups, because actually we only have two different strains, we can switch over to the volcano plot. And with a volcano plot, it's, of course, we select the condition column. We can select M1 and PA14, the two strains. And the great thing here is that now if I select any of those features, again, it's going to be selected in the table. And also I can go over to the PCA plot, and they're both linked. So if I select anything in the volcano plot, it is also going to be selected in PCA. And sometimes I feel that's quite interesting because, you know, in volcano plot it's very easy to compare two groups, but maybe you also want to see the, like, how does it map in the blanks in other samples, so you can have also the univariate and multivariate statistics basically combined in an interactive dashboard. And now we have a compound structure, but I'm actually not quite sure, like, how did mzmine come up with this structure? There's, of course, there's the similarity, there's an adduct, there's the spectral match and so on, but we all would also like to confirm basically the spectral match. In here, we can always, from the table, we can right-click and say we want to see the feature overview and ion identity molecular networks. So right-click and anywhere in the table and feature overview. And this feature overview, again, combines many different aspects. I can tell you, very often those things look quite dense because the relationships in your data set, there's a lot of different amino acids, there's a lot of different peptide breakdown products and so on. It kind of depends on the data set you're looking at, but there's a lot of spectral similarity within your samples, right? So the blue lines, the blue edges are connecting features, and they're connecting them by spectral similarity. So if we rather want to find something here, I could also just search and say, I want to search for methionine, because I know that there's a methionine in here. I can click on this focus on two nodes. So there's two features actually with something methionine. Yeah, you can also not specify it too much and then basically have like a match to just methionine here. And now again, it's quite dense, but we can filter it down. So there's the number of neighbors I want to see. And for me, like actually like doing molecular networking for some time now, I personally think, you know, you have a feature and this is significant to your data set. You might be wasting your Ph.D. kind of extracting it, purifying it, everything, and then you find out, okay, it's already discovered, right? It's something simple. It's maybe just an artifact, maybe it's an in-source fragment. So I typically see those significant features, those like prospects I want to put some effort in, and then I just open this just with the next neighbors. And the next neighbors are here defined by spectral similarity, but then also by the ion identity network. So if you see those orange edges, they're actually different adducts. For now, the annotation tells us it's methionine and N-acetylmethionine. And of course, we can say these are structurally related compounds, and we expect them to fragment similarly. They are actually connected. We can look at the spectral library matches here, and the screen is a little small here because I zoomed in for you. But you can see that L-methionine has like a cosine similarity between the spectral library on the bottom and our own spectrum on the top of 99%. And from the library spectra, actually 99.8% of the signals were also matched. Yeah, there's only 4 signals that were not matched, and they're actually very, very minor signals. Like I can zoom in, and maybe I'm gonna find like some signals that are orange and they are not matched. They don't have a partner in the other spectrum. But so the question is now, like, why did modified cosine connect these two? Of course, they're structurally related, but I cannot really find out for some of the other ones, right? Because they're also connected. I don't have an annotation for something else. Might be a new compound, might be an artifact, I have to find out, but I can always select these two. And I can select them by shift clicking multiple nodes, and then click over to similarity. And in the similarity tab, we see again there's blue signals. They are grouped and they are direct matches. And like Steffen already told you, there could also be neutral loss matches. So we could kind of just lose water, lose the same thing, but then retain the modification of both molecules. And this is the orange signals. If I want to see those, it's easier to basically flip the spectrum and flip over to the neutral loss spectrum. And then here those numbers, 46, is basically going to tell me I have a neutral loss of 46, so I can basically calculate the formula and then go annotate those spectra. So both methionine and N-acetylmethionine have the same neutral loss here. And one more thing that's kind of interesting, if you expand the table a little bit, on the right, there's actually also the contribution of each signal pair. If you actually have like one signal pair that's massive, that's really just like defining 99% of the intensity in your spectrum, and they match, they're actually also going to define, let's say, 90% of your similarity. So you're going to base your annotation just on one signal pair. This might be a water loss. There might be 2 spectra with a water loss, very intense signal, and then it's like mostly what drives your annotation. That's why people always ask me how to verify that's actually my compound. Still, we know if you have a standard, that's the best way. You inject it, you're going to know. It's very hard to get by. And otherwise, you have to like manually review. And if there's a lot of signals, it's much easier to say this is very likely the compound or very similar compound. And if there's only water loss, some not so significant losses, then you have to kind of reconsider, let's say. Or maybe use some other fragmentation technique. And just want to stretch that here, everything you can change. You can basically go for the label and say, I want to see the adduct. So you're going to see that there's the M plus H, M plus sodium, and M plus 2 sodium, which kind of makes sense if we have a lot of oxygen groups, maybe coordinating these adducts. And the other one only had an M plus H and M plus sodium. So you can always change it, the colors, the edges. We can use dreams from Roman. We can use any other method. And if you want to play around with that, you can always select the feature table. We quick search and we say molecular networking. And you're going to find that usually you're going to see a lot of parameters. We try to keep it minimal. But if we search for molecular networking, you don't have to do this now, but later, like just check it out. You're going to see that there's the DREAMS model, there's MS2 Deep Score, there's the modified cosine, And if I want to use Dreams, I only click on the download button. For me, it's going to tell me that I already have this model. I say use existing. And otherwise, it's going to download the model, and afterwards you can just click OK, and it's going to score by Dreams embedding and cosine similarity. Is going to score the similarity of all these spectra. And in the interactive visualizer, you're going to see both edges then from the one score and the other score, and you can toggle them on and off. You can see it is maybe connected by one and not the other, because they are kind of orthogonal. And so from here, I just want to highlight mostly you would be working with the table, maybe with the statistics dashboard, and always make sure to right-click and kind of see what options there are. We have the spectral database search results. They are also present, as you've seen, in the feature overview. Also, if you have lipid matches, if you're going for lipids, you're also going to see them in the feature overview, but there's also other lipid methods that you can like use for visualization. And then from here, we could now also just go back to the wizard, and we could basically do any kind of processing and go on, right? I want to highlight, you have to save some of the parameters. So I would always go, and with the wizard, if you've optimized your wizard now, I would always go and go save preset. I just type in a name and click OK. Here the directory is the default directory of mzmine. So if you put mzwizard files there, we're going to pick them up, and then you're going to be able to find them here, and you can basically just mix and match and say my 10-minute gradient with the Orbitrap. Next time, 10-minute gradient with a timsTOF. And then maybe you switch out the chromatography. Maybe you do GC with an Orbitrap, right? So you can kind of switch out the different methods as you go. So we save the preset, and even more importantly, you have to save the batch mode. Like if you want to use it, I would personally save it in a folder. If you publish your paper, put your batch file. So there's the save button here. You save it, you put it to your paper in the supplementary or in any other directory that everyone can access, and then in there's the mzmine version, there's the version of every of the modules, and then people can really reproduce what you do. And from there, we actually also have some export steps in here that already export this batch, because many people just forget. And so we basically added some steps as like safeguards to make sure that you're actually exporting the correct batch file that was applied. We also export the metadata, but you can always just add more things. You can remove things from this batch, but save it and put it to your paper. If you want to have more export method, if you want to do, let's say, blank removal, you can type in the search bar here blank, and you're going to find there's different options for blank removal. And then you could just double click, it's going to open the setup, and it's going to add it here, and I can just drag and drop and put it at the right spot. Let's say after smoothing, I want to do blank removal, and then go on with the processing. Okay? So use these files to share, to kind of harmonize the workflows in your labs, and then also, of course, to make it more reproducible. And in the publication, please don't put any tables, right? Don't put tables of like, I use this parameters, because you're always going to forget to update some of these tables. And there's usually always parameters missing. But this file is a text file. You can read it. People can drop it into mzmine, and they can actually reproduce what you did. And it's going to define everything. You don't have to write parameters by hand. Okay? Right? Sorry? Yeah, we have some time still, right? Okay, we're going to do some Q&A before. So, any questions?
So in the process of data annotation or spectral annotation, can I query for product ions or even combinations, product ions and neutral losses in the MS2 spectra to annotate my MS1 features?
Yeah, there's like currently only like a visual way of doing it. We're still working on actually integrating some of these tools more into mzmine. like searching directly for multiple different neutral losses or like of these like significant fragments, let's say. There is some way where you can right-click or you can, again, search for the MS visualizer, scatter plot. Ah yeah, MSMS scatter plot. You see, I have to search myself. So you can go for the MSMS scatter plot, and you can, it's actually, I think, a quite nice plot where you can just plot the, let's say, retention time and the precursor MZ of all the fragment scans that were triggered. It's also good quality control to kind of see that there is some masses that were not excluded from, like, with a static exclusion list, and maybe the method could be improved here to also exclude those. And then there's this little button here where you can basically search for some neutral losses, but it's really just one neutral loss. So I don't know what kind of neutral loss I would be searching for, so I will just type in something wider and apply it. And I have to resort the data points basically. And now there's basically all the MS2 spectra that have this neutral loss, but so far we cannot apply it to the feature table. But that's definitely something that we're working on to find like a very easy way of doing this, yeah. So any other questions, just point to Tito, there's one.
Thank you for the workshop. When you upload the data into mzmine and you have a rectangle with an exclamation mark, yeah. What is the issue?
Yeah, that rectangle is quite shocking to people. There's basically some warning. It's only a warning, and we try to warn you if we think there might be something wrong. There's, for example, like if you use a very old MS-convert method to convert your data to MZML, and you pick the vendor algorithm because hopefully it's the best one you could use for centroiding, but there was something else done before. Actually, the title maker was by default done before. Then it would actually use a different algorithm, and it would put zero intensity signals there. So there's a warning for this. And then also the mass accuracy would be really bad because they would just use a different algorithm that you don't want to use. And there's also warning if there's empty scans, because if we think that at least the MS1 should not be empty. Sometimes, honestly, like some of the first scans are empty for whatever reason. But then we give you a warning like, hey, there's empty scans. Maybe someone already filtered your data too much. So make sure to use the raw data, drag and drop it into mzmine, and if you get the exclamation mark and you're fine, like you did everything good in a good way, just ignore it, right? It's only an information.
All right, thank you.
Yeah, good question, yeah. There's a Kyo.
So I just check up the annotation module and find out that currently the only cosine similarity we're going to be used for the spectral matching against the spectral library, right? So why I'm asking this is I confirm that now we can use the multiple different similarity score options for the network yielding, and then why not like DreamMS or the MS2 deep score for spectral library matching? Yeah,
actually, we're just still working on it. So with this, you're going to see also spectral library matching has a lot of options because we kind of want to give you a lot of options. This one. Actually, there's a lot of options also for merging the spectra, because let's say you acquire spectra for CID, HCD, UVPD, like multiple methods. We actually do the merging on the separate methods. We're going to merge on different energies, across energies, and you can select all of this here to have like the most control. You can also just say, I want to have the representative scans, and then mzmine is going to figure out what is representative for your data set. But then, of course, there's different scores, like the weighted cosine similarity, and we still just need to add the different scores in here, and then also kind of make a decision because it's then analog matches, because it's not an identity match, we have to kind of display that in a different way that like you just directly recognize. That's identity, this is an analog, yeah? But yeah, that's going to be coming soon.
Cool.
Yeah, thanks a lot for the workshop. I wanted to ask if at some point of the wizard workflow you have implemented some data set correction steps, like either drift of the, if we use big batches, or either normalization, like, I don't know, PQN normalization, if we want to further do more relevant statistical analysis.
Yeah. So we do implement many of these things. We kind of, like when we go, for example, when we choose what to implement, especially for statistics, I can say, we did choose, let's say, the standard things, like where most people would agree, like maybe volcano plot is quite easy to use, PCA also kind of, and we try to make it more interactive, but then we also think like downstream tools are sometimes much more flexible in a way that even something like batch correction of intensities and so on, sometimes people just want to do it in their like R scripts and Python scripts, so mostly I would say many people do it downstream. We do add more and more methods, and we are very, very interested in the community actually to reach out to kind of propose also methods to us and kind of define, there's a great paper, maybe there's even implementation already, and then just define like what is the input, what is the output, and maybe how can we link it up to other things to make it more valuable than just having, let's say, an output to like a Python module. So if you search again, if you search and then again something like blank, we have like two different methods that either go quite early in the chromatograms or later on the feature level. We do have some correction for retention time, retention time correction. We're currently also working on like a new retention time correction. This is only done on the feature level, so it's correcting the retention times of, let's say, batches in your different features. But then we also want to do that actually on the raw data level, because if you visualize raw data and the features are basically, oh, the features should be at minute 9, but actually it's like kind of shifted, it's not going to look so nice, and it's going to be hard to review. And then we have like QC filters and those kind of things already in the featureless rows filter, which is a good one for filtering. And just in general, I highly recommend just reach out to us. If you are a developer, of course, reach out to us, and maybe you can even work with us directly. We can help you with the onboarding. We can help you kind of understand the code base. It's quite simple, honestly. We had some different people come in from Python. I have to say I did C++, Java, and then late Python. I was kind of opening my mind in different ways. And I had some people like who came in from the Python universe, and they came to Java, and they were like kind of like opening also, because it's a bit different, but it's the same. Like if you can program a little bit, it's very easy to get there, and you can focus on the implementation, because let's say the speed is always going to be fast. Java is just running so fast. Parallelizing a task is also super easy, because we already have a task scheduler for you, and then you can really just write your filter, your, let's say, batch correction, and it would be very easy.
Okay, thank you very much.
Yeah. Wake up.
So I have a
Thank you.
I have a question about the workflow. So I'm working in some molecules that I don't know the masses, but they have a specific isotopic pattern. So what I'm doing is a filtering based on like looking for similar isotopic patterns on my raw data and then get the possible candidates. Is it possible to do this with mzmine, and how that would be?
There's like a little bit, yeah. Maybe Steffen actually wants to take over.
I'm currently building something like that. I'll give you my email and then I can send you a test version. But like currently not in this version, but yeah, something that we can work out.
Also have to say, stable isotope labeling always comes up so far, you know. We're very focused on specific analytes and technologies and so on. Actually from like the lab where we come from, there was like a lot of different mass spec, so also ion mobility. Steffen has been building a lot of that. But of course we have our own focus. And yet now there's one guy coming in, Matthias, and he's basically building all the stable isotope labeling things, and so it's in the making. And if you have data, if you have ideas, you know, you can always reach out. We have a Slack workspace where you can also connect with him, and then you can basically just kind of work together in like trying it and also giving feedback, right?
So you have a great tool, and the wizard is very great to process the data, like deconvolution and alignment thing. But when we came to the spectral annotation, the annotation level is very less as compared to other tools, I think. So how to increase the spectral annotations with comparison to the library? It's about using multiple libraries or go with the molecular networking?
Yes. Yeah. So the annotation, for example, I mean, in this annotation tab, it's only so far there's like a local compound database search in here where you can have your own, let's say, retention time and master chart ratio pairs or maybe CCS values for immobility. And there's also options to just say I have this compound structure and it should have like these different adducts, and then we can search for it. Lipids are annotated by rule-based annotation, and with the spectral library you can actually go on this download button, and you can see that the MSNlib from Corinna and colleagues, it's basically here. You just click on download, and it's going to download either the MS2 spectra only, the MSN trees, positive, negative. There's some options here, and then you can use like much wider array of libraries. This library was kind of small, with like 150,000 spectra, and of course much less compounds. But we're also going to see with MSNlib, we already have much more compounds. So you're going to have a little more annotations. But what we also do is we export for series, we export for other tools, and then you can basically just also run like other annotation tools and get the results in mzmine or in your other like Python or whatever scripts.
So particularly I'm using your tool for the GCMS, and I find some issue with the library matching when we are comparing with the NIST one. So
Okay. Yeah, so I guess with the NIST, there's still like we're still working out with them some ways of directly using NIST also in mzmine. There is a module, but it's quite old, and we don't currently get the spectra out, so we cannot basically show you the quality.
No, the module is good, but there is issue with the matching factor. So so in the NIST we have two kinds, like match and the reverse match. And your tool is going with the match. So if the match is above 700, if we go with the 70%, so it will match the compound, but it's not the actual compound. So you have to either you have to convert, or I think I have to make some settings in my library. I don't know. So it should be with the reverse match, so it will be give good annotation. So I think you can help me with that.
It's kind of a problem with the like old NIST module and the tool that they provide. Like someone implemented that. It's also, I mean, it's a community effort, right? So someone implemented that method and then never really maintained it. And I mean, we try to maintain all the modules in there. It still works, but it was very limited in scope. So yeah, he didn't implement all the methods they have in NIST MS Search. And also, there's kind of a limitation also by the tool that, again, like we cannot review the quality because we cannot get the spectra out because they forbid that. But we're working with them on some solutions, so might be coming in the future then. Yeah. So maybe, looking at the time, I think we should also move on. And
I have one question about the lipid annotation.
Yes.
Is there somewhere specified what rules are used for the annotation? And if we have a specific lipid class that is not included, if we can add our own rules there?
Yeah, so there is the annotation. So again, I just go search lipid. You're also going to see there's a lipid annotation summary, there's a lipid ECN equivalent carbon number plot, so there's a couple of lipid-specific tools. But then in this parameter dialog, first of all, there's the different groups, and the like different rules and so on are defined in mzmine. But if you want to define new rules, you can actually also search for custom lipid classes. So you can open this, and then in here, define your custom lipid classes and rules like fragmentation and head group losses and so on. And you can always click on the help. You're going to directly go to the documentation, find some information, and if there's something missing again, please just tell us, right? Just don't silently just say, oh, that's not good. Just tell us if something could be improved, and of course, maybe even improve it yourself because it's open. So in here, one little thing, Corinna can already kind of come up. One little thing, you see I have some presets. I can always just load one of these presets, and that's usually what you would do in mzmine. You open the wizard, you load your preset, define the data files, create the batch and run it, and then we're going to just import some GCMS data, and it's also going to produce feature lists, is going to produce annotations against spectral libraries. Of course, if you have GCAEMS, it's a hard ionization. We have a lot of fragmentation that we have to take care of, and in the batch, you're going to see that because the wizard actually defines GCAE QTOF deconvolution. Deconvolution is now the workflow. You're going to see that in the batch that is generated, there is also the spectral deconvolution happening, right? In that batch, we have the spectral deconvolution, and then here we're going to produce results. You can always go and basically show a preview, and you can basically show a preview and then look at the results. I'm not going to go into that now, but we have some videos where we actually show this. So just go on YouTube. If you work on GCMS data, go on YouTube, find the GCAEMS workshop or that we did with Vimo, and you're going to find more of the results there. And it's doing the spectral library matching, and spectral library matching against the GC libraries is like a little bit slower because there's no precursor ion information, so it's a bit harder to filter down and to prioritize. But still, once you do this, you're going to see the same results, and you're going to have the same kind of feature table and kind of feel in mzmine that you have for your data analysis. And with this, we can go over to spectral libraries.
Maybe just one note for the question for the audience while Robin and Corinna do the switch.
Yeah.
We got a couple of questions about whether it's possible to query specific patterns in the data. I think first question was whether it's possible to search for all precursors generating a specific fragment in their fragmentation spectra, or the question about the isotopic patterns. Robin and Steffen showed a couple of ways you can do it in mzmine. There is another tool that recently came out. It's called MassQL, and you can it's designed exactly for doing this. And I think it's the only way you can do it at the moment with a very nice and user-friendly graphical user interface. So that's something you can check out. There's plenty of videos, documentation, and there is even a chatbot that helps you build the query. So that's an alternative for these kind of tasks, but I'm sure it would be possible to do it in mzmine soon. And with this, I'll hand it over to Corinna.
Thank you, Tito. So the next step, or the last part in this workshop, we wanted to show you the library building workflow that we are now, or that we were working on in mzmine as well. I guess most of you that do untargeted workflows, they know it's an issue to annotate actually the features in your sample set. So that's why we think it's very important to actually build the library, make public databases bigger, and that we all need to work together. So you see already that we have a lot of groups and people being collaborative, sharing compounds or sharing ideas how to actually build the libraries in mzmine and what to think about. And before I start, I think this is a very nice visualization what is actually happening. So we got the first compound library, we acquired the data, and then each node here is one MSMS spectrum. We clustered them based on their spectral similarity, so they are covered in the chemical space. And then we see each node that got an annotation in GNPS, which is the biggest open spectral library. Then we get a hit and it's highlighted in magenta. And what we see here is that most nodes are still represented in blue, so only 14% got an annotation. So we see even if we buy just compound libraries, which is something you could just buy, right? I mean, it's expensive, but you should get the annotation for most of them because it's something you can just get from a supplier and then you can acquire the data. And especially if we think about groups are working on different topics, everyone has different subjects, different compounds of interest, so we can actually broadening up the public database just if everyone would be able or willing to share the public or the spectral library that or spectral data that they acquired and make it publicly available for any other researcher maybe working on the same topic. And if we even look further into this network, we saw molecular networking in mzmine. What is also very interesting, of course, specific compound classes are very well covered in the public domain. So if we see beta blockers, for example, you have something unknown but similar, you would get an annotation and then you could like propagate the structure based on this information. Then we have the sartanes, we have less annotation, so less magenta nodes, but still you would get an idea, if this would be an unknown cluster, you would get an idea about the structure itself. If we go to the middle one with the cephalospurenes, no annotation, no ideas, so you would need to do either isolation or try to identify what is the structure in the end. Even though we see in this case is a cephalospurin, so it should be covered, it still can be covered in the public databases. Maybe it's a different instrument used or different collision energy, then we would not get a hit, but still only 14% were annotated and it's an Orbitrap instrument, so it's nothing very specific or special in this case, but still we cannot annotate it with the public databases. And this also comes with the idea, why do we have actually different motivations to build the libraries? I mean, the normal way is that you have the compound libraries in your lab, so you want to acquire the data and then match it later to your sample set. Or maybe you have something that you see very often, it's either contamination from the plasticware that you are using or from the pipette tips. So maybe that's something you want to annotate in your feature list, you exclude it during the processing, you're not dealing with this anymore. Or maybe you have something that is very interesting to you, you see it in a specific study, but you don't know what it is. So maybe you also want to export those information and then later match it to other data sets to see, maybe you see it also in other samples or other studies, and it might be important even for those analysis. And that's why we then worked on an automatic way for the processing. I mean, the data acquisition is one thing, but then extracting the library data or the spectral data out of this information is also very time consuming. So we worked on a workflow that you have the metadata, you have the acquired data, you merge everything together in mzmine, and then you do the processing, what you basically did today, and then you export everything that was annotated based on the metadata sheet that you built or that you provided with the sequence or with the workflow. In the end, you can export it in different data formats. You can export different information like retention time, collisional cross-section if you use IMS, and of course the fragmentation data like MS2, or in our case we developed an MSN workflow, so we exported multi-stage fragmentation data. And of course this workflow looks very easy and it looks very nice, but of course there's more behind it, so it's more complex. And that's when we worked on this workflow idea. So we separated in 3 different steps, and I will not cover everything in too many details. There's also the preprint out, so if you're interested about more steps, feel free to read it, and then you get maybe more ideas also about the template, how to prepare the metadata, how was the processing done in mzmine, and so on. So everything is written in the preprint. So I said we have 3 different steps, and the first thing that we found out is that you need to have clean metadata, so it means you need to have the compound name. But if you get compound libraries from a vendor, they provide you with different salt from the structure that they used. So in this case, for example, we have a tartrate, but we will not see this salt obviously in MSMS or in MS in general. So we need to remove it to in the end get the monoisotopic mass from this neutral molecule. And this is done in a Python script, so we do this the cleaning, we do the structure standardization, and then we also have the option to add additional information if you're interested in drugs, so you want to know in which clinical phase it is, or if it was found in any plant or microbe already, so we also have the option to query Lotus in this in this setup or in this Python script. The next step is the sample preparation. I will also not go into too many details. In our case, we used like a robot that was pipetting 10 compounds, up to 10 compounds in one well to have like a quick method. And then we developed a flow injection in our case to have enough time to acquire multi-stage fragmentation data for each compound. If you want to work with your compounds, of course, you can use your LC-MS setup, and then you can also do the library building, so it's not set only for this multi-stage flow injection method, so that it's just what we used as the workflow. So you see we needed like 13 seconds per molecule, which is like this tree at maximum, and that's why we went for the flow injection method instead of having the separation with LC-MS setup. The last important thing is then the processing in mzmine, and this was involved with a co-collaboration with mzmine as well. So the things that you did today with LC-MS, you can also just do, and then instead of the data-dependent acquisition, you set the system to, I actually created a screenshot, so you can set up, instead of data-dependent acquisition, you can set it to library generation workflow, and then you export everything that was annotated with the compound database file. You then export it and then have it as an individual file, and then you can share it with collaboration partners, you can use it in your lab, and so on. So I will not go in each step here, so it really depends on your setup that you used. And then the only important part is, I don't know if you can see my cursor, I get not. So the only important step here is this local database search, because this is where we combine the metadata with our acquired data. So we have an information which compounds are in which injection, basically. So we injected, for example, position A1 from a well plate, and then we know in A1 we had like these number of 10 compounds, and we would only search those in the specific file. And then from here we have like the information about the compound. We can set up which adducts we very often see in our sample. And then because everything is done automatically, we have also some cleaning steps or some processing steps that we know that what we export is actually meaningful, so that it's not just something that seems to be corresponding to the mass. So you see some steps here. I will also not talk too much about it, but it's just to actually know what is actually happening in the back. So if we know we exported something, does it really make sense in the end? So was it clean? So this you can see as a chimeric one. Was there anything very high abundant in the isolation window of the precursor, for example? And then also those information are exported with the library itself. So later on you can still see what was actually setting, or what was the purity in this spectrum, for example, that was just exported. And then you saw the feature table today, so you worked with mzmine. So we see on the left side the data processing part that you just did today. And then on the right side, we see the metadata annotation, which was done on the metadata that we provided. And then we can see this was the compounds that were found in the sample, and also the different adduct types that you set during the processing. And then from here, we acquired actually 60,000 compounds. Of course, some were like the same compound. So in the end, it was like 54,000 unique structures. And this is something that we then got in 33 days in positive and negative polarity. So we can see if we use the plate and we correlate in which polarity we detected the compounds, we can see it nicely in this pie chart. So some compounds were only detected in positive mode, some only negative, and maybe some in both, or we couldn't detect it all with our method. And this is seen also in the statistics plot here. So we used an upset plot for an easier visualization. So we see which compounds we only detected in positive mode, and most of them are actually detected in this mode. So that's why maybe most people normally use only the positive polarity. But then we also see negative there in blue, that actually like less than 5,000 compounds were detected only in negative ion mode. So in the end, it really depends. If you do untargeted, you might lose information because you're only acquiring in one polarity. Or if you're interested in one compound and you cannot see it in positive, maybe we need to go back and think about the polarity setting. And of course, ionization source, ESI or APCI might also influence what we actually see. Then on the right side, we also wanted to compare what is the uniqueness of our library compared to other databases. So we combined the open one with Mass Bank EU, Mass Bank North America, and GMPS as one, that you can use for querying. And then the mzCloud and NIST23 as the biggest commercial libraries that you can use. And they do great work, but it's just to see if we all work together, we can actually increase the public domain a lot. And you see we are almost with MSNlib, it's the magenta one, we are close to NIST23 from the unique compounds. And then if we go to the upset plot, we see that we have now most unique structures compared to other databases, but it's not a surprise because we try to include everything that we get. So also a lot of synthetic compounds. We are not like biased in only one compound class or specific compound class, because we think it's valuable if we think about the future machine learning tools. It's good to have as many compounds and structures included in those databases. And that's why maybe we have a higher number of not covered compounds in different databases, because they normally try to cover more natural products and to have those compounds included, or maybe drugs as well. But we also have like synthetic compound libraries included. And yeah, you see we got like a lot of compounds, so 60,000 compounds. That's only possible to have a lot of collaboration partners, and you see some here, and also having some ideas about the method development. So yeah, all people are involved are actually here. And yeah, thanks for your attention, and I hope if you're willing to share compounds or data that you acquired for compounds and you're willing to share, it's always great to collaborate and increase the public domain in the end. So now we acquired with MSN like 4 million spectra almost, and for MS2 it's like 350,000. So before you saw in Mona it was, how much was it, 150,000 spectra. So you can actually help and improve the library building and annotation a lot if we all collaborate together. So thanks, and then if you have any question, feel free to ask regarding the library building, or I guess still in mzmine if something pops up. I guess we still have 12 minutes left.
Any questions?
Everyone is tired from the first day. What?
We have a curiosity here.
Hi, Corinna. Do you hear me? Yeah. I was just wondering if, because I think you had 54,500 compounds, and from those you got like 47,000 MS2. So did you check more or less what are the main reasons for the missing compounds?
Is it on? Can you hear me? Yes, working. I think some compounds is just that they are not ionizable in electrospray ionization. So I also did one study to include compounds with a higher log P value, because then the polarity is not there. And then I measured them with APCI as a quick test, even though I couldn't detect all in this setup, but still I could increase by 20% the annotation. But it was just a very quick check what we can actually, or how we can increase the measurement. And maybe also we do flow injections, so maybe some compounds we might miss because of ion suppression, and so there's still something to improve. But for multi-stage fragmentation, it's the fastest way to get as many as possible out of it.
And just a follow-up question, how do you define concentrations?
Yeah, I think the project before started with getting with the NIH library, and they used 5 micromolar standard solutions, and then we started with this setup. And then in the end we were like, okay, maybe if we can get more, then the intensity is high enough to do actually nice multi-stage fragmentation, because you lose always sensitivity on the way. So in the end we decided to go between 5 to 20 micromolar if possible. Yeah.
Any more questions? Just for anything mzmine related?
I mean, that's what Robin showed before. In mzmine, you can basically select which one you want to download from mzmine, but you can also go to Zenodo or GMPS. They are uploaded there. We are also working with MassBank EU to upload them there, so you can just import them, and then you have multiple libraries in mzmine or whatever tool you want to use.
Also, if you're using some of the tools, of course, machine learning models are kind of very much dependent on that, and many of them already use the library, so maybe you're already using it without even knowing. But in mzmine, just download the library, check it out, and it is open, and you can just also add to it. So if you have compounds, if you have capacity to run standards and acquire data, just reach out to Corinna, and she's able to help you get started. There's also video, actually, which you can also watch, and she's also kind of going through more the details, like how you can optimize the process, because there's a lot of like small things that, small tricks you can actually apply. And also, if you have like if you want to find any more information, we are working on GitHub. If you have any issues, if you have ideas, just post your ideas there. I highly recommend in any community, reach out early. You know, it's not like we're going to steal your ideas or whatever. Like usually I feel like if you reach out early, it's much easier to kind of find out what's possible, what's already maybe being thought about, and then also kind of define the project much better, like if you're working on something. So let's say like a new module, some new processing, or just even like using mzmine for some specific analysis. It can be sometimes easier if you reach out early. And there's a lot of also links and information in the QR code, but also we're going to be here at the whole conference. You can always talk to us and just reach out. And also the famous Tomáš Pluskal is actually back in the corner. So honestly, we have to thank him to actually put the project on a good track. Because, you know, as a software engineer, he basically laid the groundwork of actually making it very modular and very easy to get into. We are no computer scientists, so we are chemists, and but we have a passion for like programming and software engineering. And you know, if you have a passion for something like that, it's quite easy to get into. But you also need some people kind of to give you feedback. If you're developing something and you're doing it in isolation because you're the only Python person in your lab and no one knows Python, no one knows anything there, and ChatGPT is your only mentor, that's bad. You know, no one's going to read your code, no one's going to use it later. That's really sad because maybe it's amazing what you do. And if you reach out to a community like mzmine, MatchMS, R for mass spectrometry, you know, there's for different languages, for different things, reach out to those communities and do it early. You know, like I did it too late. Like I already programmed so much, and then later I reached out to Tomáš and he was inviting and he gave me feedback for the first time to my code. And that's tough sometimes, right? Getting feedback, but it really made me a better programmer. And I guess it's the same working in a tandem, you know? So definitely, we still have 7 minutes, so I don't want to force you to stay here, but let's say like the next 5 minutes we have some questions. And then afterwards, you can always like come to the front and talk to us.
Yeah, thanks for the workshop. Almost only like conclusion words, but I just have a general, I mean, not general, but like a precise question. It makes like 2 or 3 versions, mzmine versions, that you upload the possibility to directly upload raw files. But in your presentation, in general, you always use mzdml. Is there a reason why? Or, I mean, it's one step less, or you always wonder why you always convert yourself?
I think the open formats are actually great because in a way, you know, you should always store your raw data in the raw files because maybe during the conversion there's some metadata that's lost, and you know, so it's good to keep the raw data, but the mzml file is also going to open up so many more tools. And honestly, as a developer of open source tools, we're not supposed to just basically provide access to all the different raw data files. It's too much to ask for. Actually, with mzmine, we're trying to, like, we're directly talking to all the vendors, and they're quite open to, like, maybe, like, in the future, you're going to have access to them directly. But we do use, so far, like, for many files, a converter in the background, like msconvert. You have to install it, and maybe not all of you have msconvert installed, so that's why we typically also still go with the mzml files. It is a good open standard that, you know, luckily people agreed on, and you know, you can upload it to repositories and people can basically make more out of your analysis, basically. Still, with some other formats like the timstorf raw data format, don't convert it. Like, if you're working on timstorf data, just don't convert it. It's going to be massive, and we can actually read the raw files. If you want to also use it in other tools, maybe you have to convert it, right? So that's still something.
Thank you.
So I have a follow-up question regarding this timstorf data.
Wait.
Yes, Aninda?
Regarding this timstorf data, I am also struggling with the conversion because the data file which are converted to mzml file are huge and it takes a lot of time. So do you have any suggested software which can do it and it's quite compatible to use it?
So
apart from msconvert?
Yeah, so basically, like, if you can avoid it, don't convert it. If you want to use it in other tools that need the conversion, Like there might be a new format on the horizon, but it's very far away. With mznext, get involved if you're like interested in that. Get involved in mznext and basically propose what you want to do with data, and maybe it's going to be better for IMS data. But with the iMobility, there's so much data, and the like format from Bruker is actually quite good. They are very open with their like SDKs, so you can very easily like implement it. But then the mzml also has some support for IMS data, but that is also kind of just plugged on top of it. And not every tool will be able to actually read it. The file size gets smaller. There's like collect all of the IMS in like one scan or something. But it's kind of a weird format, honestly. Like we also had to, like Steffen had to implement the support at some point.
Actually, I was trying also the data analysis from the Brukers to convert them directly to mzml, but when I'm trying those mzml to use in mzmine, it doesn't work.
With mzmine, just don't convert.
Yeah, I'm not converting. I know. I learned the hard way, so yes.
Yeah.
Thank you. That was my question.
Maybe just one last quick question, and you guys can still talk
Last
to the guys all throughout the conference.
Hi, thank you so much for the workshop. I wanted to find out how to process DIA data. I've tried recently, and I got an error that said I should at least select one feature list. And and I tried getting like guidance from online and reaching out to you guys, and I still haven't received an answer on how to get to create a feature list, or maybe there's a step that I missed or something.
No, it's easy. I can tell you, it's a whoopsie. We did add some more like security features inside mzmine. Kind of like if we save the parameters that you applied, we also want to save what kind of feature lists and raw data files the steps were applied to. And then we kind of went too far, and it basically was breaking the 4.70 or 2. I don't know, 2 was broken in the regard that's manually going through. Sometimes you couldn't select the feature list.
Yes.
But in the wizard and in the batch, if you applied it there, it should have worked. But just update to the new version, and it's going to be fine. You know, there's basically like a small bug where you could just not select the feature list in like the manual data analysis. You just go in the wizard. There's the DIA, UHPLC, or whatever workflow you do, and then DIA. Or let's say you do the timsTOF and DIA. And then, of course, there's like a couple of parameters for the deconvolution of MS2 spectra into pseudo MS2 spectra. And that's going to give you the results. Like that's going to give you MS2 scans for spectral library matching, networking, and all these kind of things. Okay. Just try it out, and there's also some videos online on this. Thank you. Give us feedback. Yeah. So it's over. I just want to thank everyone. It's always kind of straining.
Let's also thank the speakers, guys. With round of applause.
I think it's always kind of straining because you think you go to this workshop and you're going to be an expert after this, and then everything is so slow because we kind of have to like keep everyone follow. But also 2 hours is actually quite a short time. We try to do these workshops very often, and just subscribe to our like LinkedIn, whatever, and you're going to find that we post workshop opportunities in your region, like as they happen, and try to also like basically have the sign-ups there. Like the summer school is going to be in Copenhagen. There was one in Greece just now, and usually there's a lot of workshops where sometimes we also get more time to tell you about mzmine. And then there's maybe also more time to kind of cover some niche applications. Yeah, just find us, and maybe there's going to be more opportunities for you. All right, thank you.